Hello, I'm Telkind, and for my final project I did a case study in astronomy around faking images of galaxies using generative adversarial networks. The data I used for that is images from the Galaxies Zoo project, which is a crowdsourced astronomy project where people were asked to classify galaxies into having bars or spirals or being elliptical or flat, those kind of things. So in my project I'm trying to create, so I'm not trying to classify them, but I'm trying to create fake images of galaxies using GANs. Sorry. So why creating fake images? Because it's challenging. GANs are notoriously hard to train, but also because these fake images can augment existing datasets to help other neural networks to train better, because more data is better and real data is quite costly to come by. So to help you recap on generative adversarial networks, a GAN consists of two parts: a generator, shown here, which takes noise as input and tries to make an image out of that noise, and the discriminator, which tries to figure out whether the image was real or whether it was a forgery. We actually have three networks because we also have a third network chaining the generator and the detective, the discriminator, together into one network. So how do we train these networks? We do that by alternately training the discriminator and the generator. So training the discriminator happens by feeding it fake images and real images together in one mini batch, with the added labels fake or real, and then the discriminator will try to figure out or will learn how to figure out which is real and which is not. And then the generator we train by training the whole GAN network, so including the discriminator. But then we keep the weights of the discriminator fixed. So what happens is that we feed random noise here into the generator. Out comes an image, and that image is then immediately classified by the discriminator as being real or fake. So it outputs a probability. So to train the generator, we feed noise into the GAN and force a target label of the image being real. So what then happens is that the generator learns how to transform the random noise in such a way that the discriminator is most likely to output real rather than fake. But yeah, what are we optimizing really when we train a GAN? So neither the loss of the generator nor the loss of the discriminator are gonna go to zero at the same time. So because if they would go to zero, if they would both go to zero, it would mean that the forger is able to fool the expert consistently, and the expert nevertheless is able to tell all the forgeries from the real images. So that can't happen at the same time. So what we actually want is we want images that look like real images, but we also want a diverse portfolio of images. We want a variety of different galaxies. So what we want is that the distribution of the generated images matches the distribution of the real images. Now, how do we figure out whether those distributions match? That's something that I show here. So we can use the Fréchet inception distance for that. I'm not going to go into the details too much, but what we can do is we feed the generated images and the real images through what is called an inception network, which is shown here. And this inception network has a couple of layers, one in particular, the third pooling layer, which we can use to compare the real images and the generated images. So what we're comparing is the distributions of the activations of this particular pooling layer. So if those distributions of these activations are very similar for the generated images and the real images, then then we have a variety of images and they look real, so we get a low FID score. And if they're very different, then we get a high FID score. So we want low FID scores. So what did we actually implement? So we implemented a deep convolutional GAN. So that means that it has about 4 or 5 convolutional layers, both in the generator and in the discriminator. So the generator takes this one-dimensional vector of noise, feeds it through the different convolutional network layers, and outputs an image of 64 by 64 or 32 by 32 pixels. And then the discriminator takes that image, feeds it through again about 4 or 5 layers, and outputs a probability of the image being real or not. So what's different about a deep convolutional GAN network versus the usual convolutional networks? There's a couple of differences. So one is that we use convolutional strides and transposed convolution or deconvolution rather than the more common pooling layers to down or upsample. So what this does is that it allows the network to learn its own way of upsampling rather than having this deterministic, predetermined way of upsampling. Also, there are almost no fully connected layers, so it's really just the convolution layers. And we have batch normalization before each activation layer. So what batch normalization does is that it normalizes the activations in each layer to a mean of 0 and unit variance. And this helps stabilize the training and helps the gradients flow deeper into the model. Furthermore, we're using ReLU activation in the generator and leaky ReLU in the discriminator. Okay, so let's have a look at the data. So the data is 60,000 images of 400 by 400 pixels. The galaxy is always at the center. And as you can see, there are different forms of galaxies, round, these really flattened galaxies, etc. The galaxy is always at the center, so in my project I focused on the center, so I only took the middle 50% of the image. So my best experiment was the one with 32 by 32 pixels, which yields quite reasonable results. So you can see that in the beginning it starts at random noise, and then gradually it gets better and better and better, and the final fuzzy galaxies are not too dissimilar from real galaxies. So what you can see is that the Fréchet inception distance score, which is shown in red here, quickly drops to around 4, and the loss of the discriminator and the generator are around 0.7 and quite stable actually. But then when I go to 48 by 48 pixels, things didn't go so well. So what you can see here is that the images that it's generating are quite uniform. So it's always outputting the same kind of image. So it changes from epoch to epoch, but they're all the same. You can see that. You can see that also the FID score then jumps up. So it's okay at around the second epoch, but then goes up quite quickly to around 100, 200 after around 4 epochs. The losses also go down, and the loss of the generator starts fluctuating wildly. So what's happening is the concept of mode collapse. So this happens when the generator is not outputting a variety of images anymore, but outputs only a single mode, a single type of image. And that triggers a kind of cat and mouse game with the discriminator. So the generator figures out that it's able to fool the discriminator with blue images, and then the discriminator picks that up, and then the generator is forced to move to another local minimum, and then it goes back and forth a little bit. So the FID score is quite sensitive to this, which is why the FID score went up, which means bad. You can see that on the right here with some common data sets. So as the number of classes that it's supposed to generate goes down, the FID score goes up. So this is quite hard to tackle. I tried to tackle in a couple of different ways. So using different filter sizes and counts for the convolutional layers. I tried mixing in old generated images from the generator when I fed mini batches to the discriminator, so that the discriminator wouldn't specialize so much. I also tried training the discriminator more heavily compared to the generator, so training it a couple of times before training the generator again, but all of that didn't help that much. One thing that I didn't get to try, but that I would want to try in the future, is unrolled GANs. So an unrolled GAN is quite cool actually. So it allows the generator to look at the hypothetical future states of the discriminator. So what it does is that when you train the generator, you allow the generator to look how the discriminator will react to what the generator might do. Sorry, what the generator might do. So basically you're looking 5, 10, 20 steps ahead with the discriminator, and instead of trying to make the best move for what the discriminator might do now, the generator is forced to make the best move with respect to what the discriminator will do in future steps. So basically what this does is it forces the generator to make smarter moves that are not so easily counteracted by the discriminator. So you so you limit this cat and mouse behavior a bit. So you can see this at the bottom here as well. So with the unrolled GAN, the generator is able to create a variety of images, of modes, rather than collapsing onto one single mode as here in the bottom. So other potential future improvements that I could work on is, aside from the unrolled GANs, is conditional GANs. So instead of just feeding noise to the generator, you could also add a label if it's available. And then the generator would learn what kind of image fits best with this particular label. And then the discriminator is not only supposed to predict whether it's a real or false image, but is also supposed to predict the label. And this supposedly helps give the GAN a sort of kickstart. A third thing I want to figure out is that I used batch normalization just for the generator and not for the discriminator, because in the discriminator it wasn't working for me. So then the generator got stuck really fast and didn't only generated noise basically. So I need to figure out why that wasn't working for me. And the fourth thing I could try is stacked GANs, which basically means that you use one GAN to create fake images of a certain resolution, and then you create a second GAN that specializes in upscaling a low resolution galaxy to a high resolution galaxy. So that's about it for my project. I hope you found this interesting. Thank you.